Okay, so we'll talk about a bit about coarsifications of the integers. So a special case of coarsifications, and we should at least roughly get an idea what it means to be a coarse group or a coarse space. So I'll drop the definition of what a coarse structure is. It's not terribly important to know all the details. It's just saying we have here a notion of what it means for 2 points to be close. That's why the coarse structure is a subset of x times x, because it encodes which points x and y are close. And it encodes a notion of what it means to be uniformly close as well. And of course, we want x to be close to itself, which is here the first condition. If some points are close, we expect if we take less points, they are also close, which is the second condition. And finite unions, if we have close sets, we should be able to take unions of them and they should still be close. This is the third property we have here. And like the transpose, if x is close to y, y is close to x, another property which we would like. And the very last one that a coarse structure should satisfy is that if x is close to y and y is close to z, then x is also close to z, which is this very last property. The details are, as I said, not that important to remember or know. I just wanted to include the definition.
Yeah, so Leo, if I could ask, right? So when you say that the diagonal is in E, you mean that the elements of the diagonal are in E, or E is a subset of the power set of x cross x? I'm having a issue here.
Yes. Oh, thank you. E is a subset of the power set, of course. So E contains sets which we would call uniformly bounded. Otherwise, all these other things don't really make sense that I wrote down. Thank you. And the next slide is what it means, what we define boundedness as. And we call a set bounded if B times B is in our coarse structure. So B times B, the points x and y for x and y and B are a bounded distance from each other. And a controlled function is a function which sends bounded.
I was trying to just double check with Rob, but it looks like
was something said? I didn't really hear.
I think that's just background noise from someone who's not muted.
So controlled functions send bounded sets to bounded sets, and that's the property which makes these functions well defined in the category of coarse spaces, which we don't need to worry about because we work with special cases. And we say controlled functions are close if f and g, if we put it in the different coordinates and throw it in a set, if that is a controlled set. So that is in our coarse structure in the target space. And we can then talk about the equivalence class of a controlled function by just saying every function that's close to my controlled function is the same. And lastly, a coarse equivalence is just a function that has an inverse, but is also controlled. So concatenating fg or gf, we get back to the identity map, but we don't have to get back exactly, we just have to be close enough. So an easy example, metric coarse spaces, which are the ones we will mostly be talking about. So if we start with a metric space, then we can define this coarse structure here. And the coarse structure will just encode the information that we would expect. Namely, a function is bounded if it's bounded in the metric. Two functions are close if their distance is bounded in the metric. And a set is bounded if it's bounded in diameter. So boundedness is exactly what we would expect. And now we can talk about a little fact that coarse spaces are quite closely related to Bi-Lipschitz equivalence of metrics. Namely, two metric spaces are coarsely equivalent if and only if they are by Lipschitz equivalent. And the same thing holds for metrics. Two metrics are by Lipschitz equivalent if their coarse structures are the same. So if these bounded structures are the exact same, then the metrics are by Lipschitz equivalent. You don't need to worry about what by Lipschitz equivalence means. In case you haven't seen it, the definition that we have up here of boundedness works just fine for the rest of this talk, or the other way around. And now lastly, we talk about coarse groups. So we should know what a coarse group is. And we have a coarse space and we add group structure to it. And in our case, the group structure is a map. G times G goes back to G. And we have the inverse, which is also mapped from G to G. And it should be associative, but it doesn't have to be associative exactly. It only has to be close enough to associative, which is this first property that taking a different association is close or in the same equivalence class function. And the same thing, a times a to the minus 1, taking the inverse and multiplying it with our original element, should always be close to the neutral element. In our case, we don't need to worry about what the neutral element is. The neutral element in our case is just being bounded. So these two functions with respect to a should be bounded. In that case, it is well defined. And this is quite a loose way of defining a group structure. This is not really a hard condition. And that's also what makes it so annoying. But it's also really hard to satisfy that these group operations are controlled. So this right here is a condition on the group operation. Namely, bounded sets go to bounded sets. And that is such a strong restriction that a left invariant metric won't satisfy it in most cases. And what you can show is if you have a bi-invariant metric, you will get a well-defined coarse structure, which is here the example. And one special case that we can quickly talk about, the integers and the real numbers with their absolute value that we know, they are coarsely equivalent, or the metrics are by Lipschitz equivalent. And we can write down the map that does it. We map an integer to itself in the real numbers. And if we take a real number, we just round down to the nearest integer. And if we start in the integers, go to the reals and back, this is, of course, we just stay the same. This is the identity. If we start in the reals, go to the integers and back, we round down. But we only make a small error, at most 1. So the error is bounded. And boundedness we identify with the trivial map. So this is perfectly fine. And these two maps would be the coarse isomorphism in this case, because these two are also equivalent as coarse groups. Okay, now we have all the preliminaries in place. And we can see that coarse groups are really hard to study. There aren't, or almost no results are available to classify coarse groups up to coarse isomorphism. And one of the key problems is taking the nth power, or multiplying an element with itself n times, is not a well-defined function in terms of n. Each time, and this is the comment down here, each time we apply another star, we are allowed to make a bounded error, because these star operations are only well-defined up to bounded error. So each time we take another one, we can make another bounded error on top of that, which means this map is not well-defined and we can't really work with it as long as n is dynamic, but we are fine if we fix a fixed number n. In that case, we can look at the mu n, which is the multiplication by n map, and that will give us a well-defined equivalence class in the coarse functions. And in this equivalence class are all the ways we can pick associativity in this power. So the order of operations is abstracted away by taking an equivalence class, which we denote with bold faces. And the key idea is, if we have a coarse homomorphism, so a coarse map that also allows pulling the group operation apart, then we can move, this will commute with the multiplication by n maps, or the nth power maps here, which is this condition. For any homomorphism, we have this identity in the coarse space. They are not equal in the classical sense as functions, but they are close in the coarse sense. And that means the properties of this multiplication map they are preserved under coarse isomorphism. And the property that we look at is, in which cases does this multiplication map have a coarse inverse? So we define an invariant for coarse groups. For us, we pick x either as the primes or as the integers. Both these sets will contain the same information, but writing them down is sometimes easier if we only use the primes. And we just pick the set, all numbers for which the multiplication map that we just wrote down is a coarse equivalence. So it has a coarse inverse. And we can see some easy properties. By definition, the prime one is just the integer one intersected with the prime numbers. And if we have a number n in the integer case, then all primes that divide n will be in here. This may be not completely obvious, but it is kind of obvious in the normal sense, and the proof is the same. If we can divide by n, we can also divide by anything that divided n by just multiplying what we divided out too much back onto it again. So the inverse of mu p to the -1, the inverse mapping of this, we could just define as mu n to the -1, and we multiply everything we divided out too much back again. And this will be as a coarse map. This all is well defined and works out fine. So this is where the second property comes from. And now a bit about word metrics. And this is the metric that we prove our result in. If we have a generating set of a group, we can define the distance of two elements as the number of times I have to use a generator from the group multiplied on to get to where I want to be from one word to the next. So we have the word length, the number of elements from S that we need to compose our number that we look at. And the distance is just the difference. How many do I need to use to translate one word into another word? And this is a bi-invariant metric, which means we get a coarse structure. And in our case, we look at a special case, namely the generating set for the integers we use is this one. And that will define a coarse structure for us. And these can then be written down as series where each term is a power of g to the n. So they are related to the g-adic ring of integers. And here we have a bit of background, a theorem by Nathanson, 2011. The metrics for two generating sets. So SG was these g to the n, and same for SH. And these two metrics are bi-Lipschitz equivalent if and only if g to the power n is equal to h to the power m for some n and m, some integers. And this will immediately translate to our coarse setting and say that the coarse structures are the same if and only if we have this condition, the same condition up there. But that leaves a question open: when can these spaces be bi-Lipschitz equivalent and not the metrics? And this is a really hard question, and we won't be able to deal with it. What we will be able to show is they are sometimes not equal if the bi-Lipschitz equivalence that maps between them respects the group operation. So what the above says is that's the same as saying the identity, the identity map is a coarse isomorphism. That is what the above theorem says. And what we are interested in is there some other kind of isomorphism that works. And we showed that if G and H have different prime divisors, then the integers with one coarse structure and the other, they are not coarsely isomorphic as groups. So if we go back to the question, that is a lot weaker than the question we had on the last slide. We need to use the group structure. Conjecturally, we don't even need the group structure to show they are not the same, but we can't do it. But if we assume the group structure should be preserved, then we at least have a chance in many cases to show they are not the same. And what our proof does is we compute the invariant we had, and we show that it's just the set of primes that divides G. So this invariant will change if G and H have different prime divisors. And because we've already seen that this invariant is invariant under coarse isomorphism, we immediately get our claim. Okay, and to do that, we use a small lemma. Namely, if we have an integer sequence that converges to a p-adic number that is not an integer, then the word length will diverge. And this is a fairly easy consequence of, again, result from the same paper that we had earlier, where we have an integer representation where we can write each integer into this form, so a power series, and the length, the word length, is just given by the sum of the absolute values of these. And what we did is we extended this representation to the p-adic ring of integers, but with the condition that this might be infinite. And it will be infinite if and only if our number that we approximate is not an integer. So if x is not an integer, then this length will be infinite. If x is an integer, it will be finite. And a key thing that we need is if x and y are in the same congruence class for a large enough power of G, then these terms that measure the length are equal. And those are quite easy to conclude from the original paper. It's fairly easy properties to check that all of this works out and is well defined. And once we have this, we can just straight up compute our invariant. And what we want to show is if P is a prime that divides G, then then this prime is in our invariant. And the nice thing is our invariant was closed under division. So it's already enough to show that mu G or G is, so we want to check this. And we immediately get all the primes that divide G are also in there by the properties of the lemma we had earlier. And in our case, we can just write down the inverse. It's just x over p and round it to the nearest integer. And just looking at this, it would seem like this would work for any prime. Doesn't matter if it divides p or not, but we have a condition to check. The inverse has to be controlled. And this is also the condition that breaks in the cases where our d primes are not in the invariant. In our case, this condition that it's controlled just boils down to showing that the inverse map that we just wrote down doesn't make the generators explode. And we can compute them explicitly. From plus minus 1, we go to either minus 1 or 0. And from plus minus g to the n, we go to plus minus g to the n minus 1, because we just divide by g, not p. And then we show that all primes that divide G are in our invariant. And the other way around is a little bit more tricky, because here we now need to show that our inverse map cannot be a controlled map. And the property we use is this one. If we have a coarse equivalence or coarse isomorphism, then pre-images of bounded sets are also bounded. Just the way that images of bounded sets are bounded, if we have the other map going in the other direction, pre-images also have to be bounded. And we just write down a set and show the pre-images not bounded. And we pick this set. We take our element G to the power p minus 1 n minus 1. And this p minus 1 is needed because G to the p minus 1 is congruent to 1. So taking it to the power n, it is still congruent to 1 mod p because p and g are coprime. And therefore, the prime p divides all these numbers exactly. And we can directly compute the pre-image under the multiplication by p map, which is just given by this set here. But if we take these elements as a sequence in n, then we can show that these will be congruent to minus p to the minus 1 mod high powers of g, because we can view the inverse of p as an element of the g-adic ring of integers. And now we can use the small lemma we had. We have a sequence that converges to a number in the g-adic integers, but that number is not an integer itself. And that says now the length of this number has to explode to infinity. So this set B that we wrote down, if we take the pre-image, that has an accumulation point at minus p to the minus 1 and is therefore unbounded because the length of the elements diverges in the word metric. And that completes the proof. We have now seen that the map cannot be a coarse equivalence and the prime is not in there. So that's already enough to show that two of these groups are sometimes not isomorphic, but we can't do all cases, and we'll get to the open questions that we can't prove at the very end. And what we'll do now is we'll take a look at one more way to define a coarse structure on the integers, which is coming from the p-adic topologies. Namely, we can take the pro-Q completion, so taking a projective limit, or just defining it as the product topology here, which is, I think, intuitively the quicker way to define it. But under the hood, these are also given by a projective limit. And the special cases are when Q is just a single prime, then we have the p-adic integers. And when Q are all primes, we have the adelic ring of integers. And we can also compute the invariant for a coarse structure defined by a topology. Namely, for a topology, we say a set is bounded if it's relatively compact. This is what this says. The definition is not terribly important. Boundedness means relative compactness. And if we take the subspace topology of one of these and put it onto the integers, then the integers are no longer a compact set. Because we only pull the topology on the integers, we don't put the points from the p-adic integers in there. We now have sequences which don't have limits in the integers, and these are not compact or relatively compact. So we have an interesting coarse structure. And our theorem is, and this time we are able to completely solve all the cases that are available. If and only if the two sets of Q are equal, then the coarse structures are isomorphic. And the only thing we need to do is compute that our invariant is equal to Q. And once we have this, the theorem immediately follows. And if P is in Q, we can compute the inverse of our multiplication by P map explicitly. Again, there is a little bit of annoyance in showing that it's controlled, but this works out just the way it did before. And interestingly, this map is not only controlled, it's even continuous in the p-adic topology, which was kind of unintuitive for me because I didn't expect it. But the congruence classes mod P are closed and open subsets of the p-adic numbers. So we can check on the congruence classes separately, and in these congruence classes, if we fix one, this map is just addition and division. And there is no rounding involved, so they are continuous. And going the other way, if P is not a prime, idea is exactly the same. We construct a set with unbounded, that's bounded with unbounded pre-image. And this time the idea exactly the same. We take a sequence that converges to P inverse. Because P is not in Q, P inverse is an element of Z big Q. And then we can write down this set B. And because Xn converges to P inverse, P times Xn just converges to 1. We put the 1 in there. So this is a compact set in ZQ, which means it's bounded in G because it's relatively compact. But we can take the pre-image explicitly. The pre-image is just reversing the multiplication by P. We have these Xn, but they now have an accumulation point at P inverse and is therefore not relatively compact because we can't get the accumulation point back because we are only in the integers, not in the p-adic ones. So the map mu P is not a coarse equivalence, and we have proven everything we need to show. And those two theorems are all we showed in the paper, and there are quite a few open questions. What can we do? What can we not do? And I'll talk about those a little bit. And the main conjecture we would expect is these two coarse groups from earlier, the first theorem I talked about, they should be coarsely isomorphic if and only if this condition is satisfied, because this is the condition we know where the identity works. We would expect that this also works in general. At least I would expect that. And I would hope it's true. Maybe it is not. We are not able to show anything in that regard yet. Then we reduce the easiest still open case in that setting from S2 and S3 now to S6 and S12. That's because we need at least two distinct primes. And one prime has to appear with a different power. So that's where 6 and 12 come from. They are the smallest choice of integers where we cannot show that they are either isomorphic or not isomorphic. This one is still open. And then, of course, even more general, the conjecture that was already in older papers that we didn't come up with, do we even need the group structure to show that they are isomorphic? Or in this case, by Lipschitz equivalent would be the analog from the number theory world. And all of these are still wide open. At least our approach will not be able to handle this case. We can't do it, even if we expect to extract all the information contained in the multiplication maps. This one is out of reach. Our methods will not be able to tackle this. There's no hope to get there right now. And then we have a few more open questions that one might consider. Namely, can these metrics that come from a word metric ever be coarsely isomorphic to a coarse structure that comes from a topology? We also expect this to not be true. And our invariant already gives the only candidate for Q that can be the right one, which is Q has to be the primes dividing G. And then in this case, our invariant can't tell if these are the same or different. And we can't tell by checking by hand. We tried, but we can't do it. So this is also open. And then lastly, this one is a little more abstract and not really related exactly to what we did. If we have two variants of maps, either one coming from a metric or one coming from here, anything is fine. We would be interested in any result in this ballpark. Is there a homomorphism that's not bounded and also not coarsely surjective? So it gets close to any point. So pick a bounded set for every point in the integers, we land a bounded distance away from it sometimes. And those are all the open questions. In case you have inspiration or ideas for any of these, you are, of course, you can try. We don't have any big ideas on how to go further from here. Thank you.
Thank you.
Thank you.
Are there any questions for Leo? So I assume this is work is sort of disjoint from all of your work on while sums and the circle method?
Yes, this is completely different.
And
But it was a really fun project. It was nice. If you get stuck on one problem, it's so nice to have another problem in the back that you can divert a bit of attention to if it doesn't work out in one of your projects. And this is
how did your author Federico get interested in this or involved with this?
he wrote a book on coarse groups, which
Yes.
is, you can see it down here. And one of the conjectures that we solved was a conjecture in the book. So that's how we got started talking about this. We were interested in the special case where the Cayley graph for S2 and S3. We wanted to look at those. And from there, we managed to find a way to do it for 2 and 3. And we generalized it into this setting where we have the invariant that can do many of them at once.
But does he have any particular number theoretic interests?
I don't think he really had too much number theory interest. Or maybe he does. Maybe this got him interested and he will continue to do more in this area. I'm not too sure. He does a lot of work on more abstract. This was just a special chapter in his book on the integers and how to coarsify them. I think he works a lot in row algebras, which I don't know anything about.
And there's this now old conjecture or question of Richard Schwartz about quasi-isometry on the integers when you look at powers of 2 and powers of 3. So does that intersect your work at all?
I had thought about it a lot, actually. I found it quite interesting and I thought about it. We are able to solve this in the group case. So if the quasi-isometry roughly preserves the group action, it cannot exist. This is what follows from one of our theorems, but it's so hard. If you don't have the group structure, your map can be wild and there's no way to get a good grip on it. And it feels way too far out of reach for any progress, at least to me.
And in your paper, I think you reference an article by who is it?
Wait,
where is it?
I don't have my window.
No. I thought there was something by Borisov. But who's here? So, don't know why did I think that? Other questions for our speaker? It's very interesting. To me, it's interesting that someone resuscitated these ancient papers of mine that I thought had been deeply buried in the literature and resting in peace. But
we originally proved the thing where the length diverges ourselves, and the proof was, let's say, not pretty. And we found out later that using this paper actually makes it quite easy. So we rewrote our proof into that setting.
Okay.
And
let's see, can you stop your share screen since
Yes.
that way we get to see everyone's nicely? Questions or comments? I
Well,
remind
I
you
noticed there are a lot of coarsifications of the integers. You said 2 to the 2 to the omega,
Yes.
alpha naught, or whatever. Are there interesting coarsifications? Quite interesting natural coarsifications, quite different from that are arising from number theory, would you say?
The number theoretic
With all
ones,
your regards.
you can, of course, pick any Cayley graph. Any Cayley graph that you define will give you one of these coarsifications, because any Cayley graph will give you a bi-invariant metric as long as it's the set you use as a generating set has the inverses and neutral element in there. Then you get a bi-invariant metric and therefore also a coarsification.
What if you do it with a semigroup? Just do it on the positive integers. What happens then?
I don't really have an intuition what happens in these cases. These are also quite open, I guess, in number theory when it comes to bi-Lipschitz equivalences.
I meant no harm with the remark.
Oh, no problem. We already thought about what happens if we take 2 primes, so G and H, and we take the generating set with powers of G and powers of H. Those are, I think, also quite open in the number theory case, and no chance in the coarse setting because all our invariants, we can't really compute them anymore. We need to somehow have this nice Cayley graph to even approach the invariant and get some results.
When you're looking at 2 elements being close together in some sense, is there any non-standard method that would be might be applicable?
I thought a bit about rewriting the closeness. At least if you are in a metric setting, you could rewrite it as asymptotics. So you can write your bounded error as big O of 1 and carry it around all of your terms. It didn't feel too promising. It might be possible to recover the taking the nth power, at least in an asymptotic setting, where if you make the variable x that you're taking the power of big enough, then it will be well defined no matter how large you pick your n, as long as your x grows together with the n. But it's also really hard to get a good grip on those. And I haven't really seen a way to use these to get any good results.
Yeah. Whenever I see David Ross, I think I have to ask whether non-standard analysis could be useful. So, it's like Richard Feynman tells the story of why he's considered such a great physicist. He would walk around with a list of 10 problems in physics he wanted to solve. And any time he heard something new, he would take out his list and see whether it applied to any one of his 10 problems. And every now and then there would be a match, and he wrote it down, and they said, oh, he's a genius. But he said, it's just because I always carried this list of 10 problems with me. So
that's a necessary but not sufficient condition.
uh-huh.
I carry a list of 10 problems with me. They're the clay problems, but it doesn't seem to work.
Oh, there are only 9 of them left.
That's okay. It's 9 too many.
Right. And one of them wasn't even well defined. So, yeah. But I always thought about that. It was really an insult to mathematics. These Wall Street guys pay their secretaries $1 million a year. So to give that amount of money for the Riemann hypothesis really, I don't know, like downplaying the importance of it all. But okay, so let me remind you, next week there's no seminar, and then we have 3 more seminars this semester after our little break. We do have 1 or 2 openings in case anyone whose initials are AB might be interested. And I think the last seminar before we start, there's a tiny break and then there's the CANT conference. I think whenever it is May 9th or so, Florian Luca is speaking, and that's the end of our semester. I've been somewhat remiss about advertising the CANT conference because life is short, and I'm so far behind in things I was supposed to have done several months ago that I haven't done too much about the CANT conference. But we already have enough talks. We have talks, so it's not so bad. But I would
What
like.
is Florian speak? What is
What?
Florian speaking of? Do you remember offhand the title of Florian's talk?
It's on the seminar list. I don't remember.
Oh, okay.
Oh, sorry. I know his title. His title is I know his title exactly. It is to be announced.
I've heard that lecture before.
I thought it was to be or not to be announced. That is the question.
No, he's reliable. It will be announced. But
Well, Hamlet was reliable also.
yes. Yes.
Anyhow, nice talk and stuff. I feel there must be really great problems having to do with course groups.
Yeah.
Oh, there is this thing. There's another notion. This is like almost groups. Almost.
Oh, you don't mean that, what the hell is it called?
It had the word almost in it, I think. But it's another approximate groups.
Yeah, approximate groups. So,
So
yeah.
the issue is to relate approximate groups to the course groups. That sounds like a fair question.
Yeah, no. That was like, that was Terry Tao and someone's notion, maybe Ben Green, Terry Tao. They were writing about approximate groups, and then there was some generalization of it.
The subset of a group that behaves like a subgroup up to a constant error. So it is a course note kind of notion.
Yeah, I mean, I
There's a
generalize it
Wikipedia page on
somewhat.
it. There's a Wikipedia page on it, and I bring that to the attention of the speaker if he's still here.
Yeah, no, he's
Yes.
here. I mean,
That sounds very much like it would define a course group, because that's exactly what course means, up to uniformly bounded error, your group.
Except the thing isn't a group. That's the point.
It's not a group.
no.
The subset of a group which behaves like a subgroup in a precise quantitative sense. So there's a Wikipedia article on our US Wikipedia called Approximate Group. So you can look it up.
So does it sound like a coarse subgroup of a group which is considered something like that, right? Because it's like a
So-
coarse subgroup of a coarse group.
Oh, Lord.
I'm only trying to make the connection. I'm not trying to solve the problem in real time.
Mhm. Must be related though.
Wait. I have to show you something. If I can find
Up to a bounded error.
Yeah.
As far as I know, the notion of subgroups in course geometry is not that well developed, but that
All
sounds
right, course subgroups.
yes. Course subgroups I haven't really encountered and worked with. That might be the definition that's used, or I don't know if it is used widely or widely.
It says that
available.
approximate subgroups of Z were completely classified by Ruza and Freiman. So they have a theorem in this article. All right.
Oh, here, hang on a second. Let me find something.
So at some point you should stop the recording. Huh?
Oh, thank you. Let me do that. If I can figure out how to do that. Stop.